Yes, so welcome everybody to our last seminar on the reading of the ultrascale playbook. Today we're covering the very last chapter on fused kernels and mixed precision, and they will also try to incorporate some relevant information that I found interesting in the context of this chapter. So here's our plan for the talk. As was announced in the chat, we will start with fused kernels. I will just briefly cover the idea. Then we'll briefly cover the flash attention example that's given in the book. But I think that flash attention is like the most common example given in this context of fused kernels. And it's also very important in the context of machine learning interviews. So like, it is my understanding that most of the folks that are interested in this topic, they have already read something about flash attention. They understand at least some of the parts of this mechanism. So, and I will thus cover one less common example, which is like somehow similar to flash attention, but also expands on the idea of using fused kernels to increase the performance or decrease the memory consumption. Then we'll talk about data types and how they can be used to do mixed precision training. We'll again cover what's in the book, which is 16 or half precision bit training. Then we'll cover the recent advancements in FP8 training. And we'll talk a little bit about our nearest future of using even more extreme quantization techniques to train the models. So starting with fused kernels, I really like this picture. I believe I've seen it for the first time in 2021, maybe 2022, and it's like self-explanatory. On the left, we see how the compute pipeline works in the common sense that you just write some operations. There is a sequence of computations. It might be a linear layer followed by some nonlinearity function, then again linear layer, etc., etc. And as we have learned from the book in the previous chapter, there are different types of memories. On the GPU chip, there is a big chunk of DRAM memory, which is relatively slow. It's still faster than your hard drive, for example, significantly faster. And it's just enough to store some data to be then transported into the compute units that do the math within the GPU. And on the right side, within every of these two images, there is compute, which is basically some compute units plus very fast memory. It's called SRAM memory. It's memory on chip that has significantly higher bandwidth. So on the left again, we do a sequence of computations, and after every piece of computation, we store the data from the compute unit back into the memory, even though this result could be needed just for the next operation. So there is an obvious optimization. Let's not store something that should be reused immediately, and we can do sequence several operations in the compute unit, and only at the end of this sequence, we store the data back into the memory. So instead of doing back and forth between global memory and compute units, or very fast SRAM memory, we will try to pack as many successive compute operations as possible together in a single kernel. And kernel, a reminder, is just a program that runs in parallel on GPU. Yeah, basically a compute program. Some additional information. So obviously, the bottleneck here is that the amount of memory that lives near the compute units is very limited. And in the next slide, or like somewhere in the near future, I will cover the volumes of this memory just to give you an idea how you could design this trade-off. So from the first principles, if you want to chain several of the operations together on the compute side so that we don't store the data back into memory and then load it again. So from the first principles, it seems that this is especially efficient for successions of point-like operations that are performed independently on each each input token. So in other words, for example, an ideal candidate here could be applying nonlinearity because it's like applied on every value that you have, and they are not connected in any ways. So in this case, there is no point in sending the compute values back to the global memory before moving them to SM memory and spinning up a new kernel. So you can fuse them effectively and do two computations, two operations at once, and only after that store that into the DRAM memory. So it's good for LLMs because in a transformer model, fusing can be applied in many layers and parts of the layers. So the example that's given in the book is layer norm, but obviously some of the recent transformers have other type of normalization, which is, for example, Hermes norm. But also there is like a huge variety of operations depending on your architecture that could be fused. One example is fusing non-linearity, as I mentioned several times already. For example, Gelo or Sviglu. I'm not sure I'm pronouncing the names correctly. It might be Gelo. I'm not sure. There are sometimes gating mechanisms that also could be fused. I believe Tridao, the author of Flash Attention, recently released a whole mixture of expert kernels, which fuse altogether the communications and the computations, including dispatch, grouped general matrix multiplications, and combine at the end of the mixture of experts. And like all of that is presented as one kernel that's launched across the GPU fleet. As we go from full precision or half precision training to more aggressive quantizations, there is this thing called quantization on the fly, where effectively you have something in higher precision, then you downcast it to lower precision, do some computations, then accumulate the results in higher precision and return the result in higher precision. So effectively, we are doing the mathematics in lower precision while everything stays in the higher precision. And this quantization on the fly could also be fused with some of the operations. So like effectively, this is one operation where we do the quantization, then dequantization, and there is computation somewhere in between. The new way of doing the positional encoding that was introduced maybe 2 years ago is rope. And it also can be fused with the computation layers of your transformer. Obviously, there is flash attention, the example that's given in the book, and I already announced on the plan slide. We will also cover it. And there is a fuse kernel that effectively fuses the computation for the cross entropy with the LM head, which is the last layer in the transformer, which basically encodes the embeddings that your decoder stack produces or encoder decoder stack produces, depending on your architecture, with the final classifier that produces firstly scores and then probabilities for the tokens to sample. So flash attention. On the left, there is this hierarchy of memory that I have already mentioned. HBM memory is relatively fast. It's much faster than the DRAM memory, but it has relatively high capacity. Like, for example, 40 gigabytes for some past generation GPUs like A100. H100s often have 80 gigabytes on board, and GB 200s, 300s, I believe, even more, like 192 gigabytes of memory. So this is the number that NVIDIA advertises. But there's also a very fast on-chip memory called as RAM. It is very limited. In case of A100 that's mentioned in the original Flash Attention paper, it's only 20 megabytes, not gigabytes, but megabytes. So we see a huge discrepancy here in the amount of memory, and we should be very careful with what we want to put on this memory, on-chip memory. But it's also very fast. It's 19 terabytes per second for, again, the Ampere architecture. And here, just out of curiosity, I pulled up from the internet, from the NVIDIA spec, the numbers for Blackwell architecture, which gains traction like right now. These GPUs are available for rent, and like most of the open source libraries already support the training and effective training on these GPUs. So SRAM memory has increased more than 50% to 33 megabytes, and the speed has also increased 2 times. So basically, the bandwidth is bigger, but also the amount of memory is slightly bigger. And I wasn't able to find numbers with Vera Rubin, but like rest assured, this is NVIDIA and we're in the scaling age. So I believe these numbers should go up and to the right. So the memory gets faster and there is more memory. So what's the trick with flash attention? I will try not to cover in detail all the optimizations that were proposed in the original paper and more importantly, in the consecutive flash attention 2 and flash attention framework, but I will just remind you guys what's the main idea and what are the main savings come from. So if you recall how we calculate the attention matrix in the transformer, we basically have a number of tokens n, and we want to check how each of them attends to every other of them. We also can apply masking, so the tokens do not look into the future, they only look into the past and attend to the tokens before them. For example, token with the index 5 will attend only to the tokens with indices from 0 to 5, only 6 tokens, including in themselves. So we have this square matrix of relationships between different tokens. There is one matrix per layer per attention head. So all in all, we have a lot of these matrices. And if you expand the context length during the training or fine-tuning or even inference, well, this means that you have to store these huge matrices in the memory. And more importantly, you have to bounce them back and forth between very fast but limited SRAM memory and HBM memory. And we actually have two of these matrices. So the first one is the matrix of scores before the softmax, and then we apply softmax and we store the probabilities. So here's the diagram from the book. Originally in the HBM, we somehow have computed queries, keys, and values in each of the layers. Then we pull up the queries and keys into the really fast SRAM memory, multiply them, do not forget the transposition, obtain the square matrix of scores S. We store it back to the HBM, which should be a bottleneck because again, this matrix for long context is pretty huge, and this operation of storing will take some time. Then we just wait a little, launch a new kernel to compute the softmax. We take this stored matrix and pull it back into SRAM. You can see where the optimization could happen. Then we compute softmax, produce the probabilities P, and then we store them again in the HBM, only to pull them out in a SRAM back alongside with values to produce the output of the attention layer. And then this output is stored into the HBM, so the future computations could happen. So you can see that sometimes, like 2 times within this diagram, we do this relatively stupid thing, right? Where we compute something, store it back into slow memory, then pull it back from the memory just to do the computation. And flash attention just aims to fuse this all together. So to avoid all these errors before we get the output, which could be stored in HBM, thus avoiding a lot of memory bandwidth reads and writes. And I love this table from the flash attention paper because it explains what's the trade-off here. So there is standard attention implementation and flash attention implementation with optimizations. On the first row, you can see the amount of flop, or basically the amount of mathematical computations that this kernel has. And you can see that flash attention performs more mathematical operations. So it should be, naively thinking, less effective. But it turns out that because we optimize the reads and writes for the relatively slow HBM memory by 10 times, the runtime for these kernels differs significantly. Flash attention is more than 5 times, like approaching 6 times faster than the naive implementation of attention. So even though we do more computations and reading a little bit ahead, we do more computations because we need to recompute some parts of the values here in the on this diagram, we avoid a lot of stores and reads or reads and writes, so that instead of transmitting 40 gigabytes of data between SRAM and HBM, bouncing them back and forth, we do only 4 gigabytes of reads and writes in total. And flash attention is not optimization in the sense that it changed something about the attention itself. It's precise calculation, meaning the outputs should be the same with the correction of the order of computations, because we all know that GPUs are not deterministic, and like maybe it's not bitwise identical, but like mathematically it's identical. There is no optimization of the mathematical level in a sense that we are changing the way the outputs are computed. Yeah, so on the right, you can see the diagram that explains how flash attention works. I will not go really deep through it because I assume that most of you are like familiar somehow with this work, and B, there is a really great explanation which I will mention on the next slide. If you haven't read it, like I advise you to read it. So as I mentioned, the key element is to compute a large square matrix of scores S. But flash attention does this in pieces or tiles, as we covered in the last lecture. And these tiles could live in shared memory. This is colored in orange here. So everything in green stored in the slow memory, then it gets copied to the fast memory. You do some computation in the fast memory and store to the slow memory without doing back and forth. So it's like one read, one write. And yes, you can iterate over some of the chunks of the data several times, meaning they will be loaded several times. But there are like some optimizations to minimize that overhead. Yeah, one immediate question that probably could arise is that during the training, we should not only do the forward passes, but we also need to do backward passes. And it's very important to store the activations for the backward passes. And I believe it was the very first lecture where we talked about the gradient recomputation, or gradient checkpointing, it's called, or activation recomputation. the name. So it also is applied on flash attention. And so the idea is that we can not store or drop completely some parts of the computation and not store them back in the slower memory, but then during the backward pass, compute them on the fly again. And this is where the computation overhead comes from. So good old computation to the rescue to minimize the amount of memory bandwidth we're using to calculate the attention kernel. And as a result, this fused flash attention kernel includes all the same computations that we are doing for the naive implementation of attention, but it runs significantly faster. And on the right, you can see the link, which you can find on the share slides that I will share after this talk, by Alexa Godrich. I believe he has worked for DeepMind at the moment, at that time of writing this blog post. So really in detail explanation of all the math and optimizations that were done in original Flash Attention. Yeah, and in the book, at the very end of this chapter of Flash Attention, it reads, all variants of linear attention and subquadratic approaches to approximate attention developed shortly after the invention of the transformer architecture have mostly been put aside in favor of the exact and fast flash attention implementation and mechanism. So for some time it was true, it has been true, but I believe right now, as Ilya Satskever put it recently, we are moving towards the age of research. And I believe there will be many more changes in how we compute the attention. So even if we take DeepSeek's V3 model as an example, it had a modified attention, multi-head latent attention, and they proposed sparse attention. There was recent change in DeepSeek V3.2. So different players try to play differently with this attention, and maybe flash attention also has to change in the nearest future in order to keep up with the developments and the age of in the age of research. But we will obviously not dive into the like different types of attention and like the optimizations for them. That's probably even we should book a time not even for a lecture, but for a whole course of optimizing attention, different types of attention. So as I advertised, I will not dive too deep into the flash attention, but what we will cover in detail is another fused kernel that's often used right now under the hood, and most of the folks are not aware of that. It's called fused LM head and cross entropy. It was proposed in the cut cross entropy or CC paper by Apple, interestingly, in the end of 2024. And that's basically a method that computes the cross entropy loss without materializing the logits for all tokens in the global memory. And rather, it only computes the logit for the correct token and evaluates the logsum exp over all logits on the fly. So what essentially this means, if you recall how we train the models, at the very end, we compute the cross entropy. And if you recall the formula, how we compute it, it says that we need to take the probability only of the ground truth token, right? So we don't need everything else. But in order to compute the probability, you obviously need to compute the logits and then take the softmax. So basically, we need to do the computation, but we don't need to store them. And this is very analogous to how we have optimized the flash attention. So we can drop most of the data, most of the things that we have to remember only to do the backward pass later. We can compute them on the fly and instead store very little information. And on the left is the plot from this paper. It's somehow very similar to what we seen on the very first lecture of this course, where we were analyzing the amount of storage dedicated for different parts of the model weights and gradients during the training for forward and backward passes. And for different architectures, you can see that for smaller models, for example, GPT-2, the storage dedicated for log probabilities takes up like 90% of the, it's probably for GPT-Neo 1.3, not GPT-2. I'm not sure which name this circle should have. But anyways, for this model, is either it's GPT-2 or GPT-Neo, the log probabilities, as you can see, take up to 90% of the memory. So if we were somehow to completely drop them and not lose in the computations of the cross entropy, obviously we can effectively significantly increase the batch size, thus increasing the stability of the training. And even for bigger models or more recent models, that's also true. For example, for llamas and gammas, log probabilities, even for 8 billion model, could take up significant portions of the memory. And the idea of fused kernel is to avoid this storage specifically for the probabilities and then scores, or first scores and then probabilities that are used to compute the cross entropy. And here on the slide, on the table on the right, you can see the three columns that are interesting to compare against different baselines and implementations. So there is amount of memory and time dedicated to loss gradient and loss and gradient, because we need to, in case you need to train a model. So in an if implementation, even if you do not use the torch compile, you take up to 24 gigabytes of memory for, I believe it was Gemma 2 2B model that they were training with vocabulary size of 256,000. It has been trained on a batch of 8,000 tokens, and the hidden dimension for this model is around 2,000. So for these numbers, they run the baseline in PyTorch, and it took 24 gigabytes only to store. So it's 24 gigabytes not for the whole model, it's only for the log probabilities. And gradients for those is additionally 16 gigabytes. If you do the training, obviously there are some optimization under the hood in PyTorch. So the total will be for loss and gradient, not 24 plus 17 plus 16. It's only 28 gigabytes. But that obviously could be optimized. So the proposed solution, which we'll cover on the next slide, is significantly reducing the memory footprint, especially for the loss, as you can see from the table. So how do they achieve this? It's somehow similar again to the idea of flash attention. So let's recall what we need to do in order to compute the LM head and then follow it by cross entropy. On the very top in orange, you have the embeddings that are outputs of your decoder stack. These are basically just a batch of hidden representations of the tokens. And then you have a classifier head, which is basically the size of the hidden state times the vocabulary size. And then in order to compute the cross entropy for the ground truth token, obviously ground truth tokens could be, there is only one token for one ground truth token for one input token. And this means that for every input token, you should load not the whole classifier head, but only some of the rows from that matrix, which is depicted here. So from the classifier head or LM head, we just pull up some of the subtensors, and then we concatenate them, and then do the product multiplication in order to obtain the scores for the ground truth token. But obviously, scores are not enough. You also need to compute the denominator for the softmax, and this is what is called linear log sum exp. It basically works the same way, but there is no index load because we need to go through all of the tokens, meaning we need to chunk the classifier head or LM head into the smaller tiles and then do the multiplication and accumulate the results. And there is this formula that is used to update the representation of the numbers in the denominator on the softmax. If you're familiar with flash attention, that's basically like the same thing. So yeah, as we are moving to the training part, so we obviously need to compute the gradients for that. And to compute the gradients, we usually need the activations. So we need to recompute the same values on the fly because we're not storing any part of the computations that I mentioned before, other than the output results, which are the probability scores of the ground truth token and the denumerators that we should be using to compute the softmax for this ground truth token. And the computations here are a little bit tricky. I will not dive into the algorithm of computing them and updating the values on the fly, but rather I would like to point out that because of the vocabulary size of the current generation models is so huge, you will do a lot of additions here. So basically, because you chunk every piece of every matrix you have as input for the separation, you have to allocate some intermediate buffers, which are used for accumulating the gradients for both weights and activations. And gradients for activations is the downstream gradients. So you can imagine that you will do a lot of additions here. And this could be problematic if you use some of the lower precision techniques, which we'll cover shortly. But before that, we obviously need to understand, like, or just remember what are the data types that are used to train large language models or neural networks in general. So as I hope you probably all know, the numbers are represented in computer in form of zeros and ones or in binary notation. And if we take as an example the regular precision, which is floating point 32, it allocates 32 bits to represent a number. One is dedicated to storing a sign, either positive or negative, 0 or 1. 8 bits are allocated to represent the exponent, and 33 bits are allocated to represent the mantissa. So exponent is this number in this formula. So this is how the binary representation could be converted into something very similar to scientific notation, but in difference with say scientific notation, we are using 2 instead of 10 as a base for the power here. So sign is 1 bit, then exponent represents this number e. We compute this number using this binary representation, do this shift by 127, and the result is the power of 2. And obviously, the bigger your exponent here, the bigger the number here, so the greater the value that you store in the computer. And mantissa is essentially responsible for the resolution of the number that you are storing on the computer. The more bits you have here on mantissa, the closer are the numbers that you can represent, which we will cover on the next slide or the slide after that. So in addition to float 32, I believe it's like 5 or maybe even like 7 or 8 years ago, it has been found that obviously for some of the parts of the computation, you can be more effective and use half, not full precision, but half precision numbers. So it has all started with float 16, which assigns 1 sign for the 1 bit for the sign, only 5 bits for exponent, and 10 for mantissa. So the resolution will be lower, but also the range that you could represent will be lower, as we will see on the next slide. And some time ago, I don't actually remember when this happened, but Google Brain, before merging with Google DeepMind, they proposed this format called bfloat16 or brainfloat16, which again uses only 16 bits or half precision to represent a number. The sign bit does not change, but the exponent has the same range as full precision, 8 bits here and 8 bits here. And we essentially allocate only 7 bits on the mantissa, which means the resolution will be smaller, as we will see on the next slide. So what's the resolution anyways? So let's take as an example the range between the interval between the numbers 1 and 2 and try to print or just plot on this graph all the numbers that could be represented with different data types. So for float 32, we see like we can represent a bunch of numbers, and only towards the very left part of this plot, the very small numbers, 1 plus 10 to the power of minus 4, we see these gaps between the numbers. So effectively, the computer cannot represent number, for example, here in between these lines. It should be rounded either to this number or this number. The same applies to all the data types, but because we allocate less bits of information for every of these data types, the data becomes more scarce. And for example, or for float 16, around 2 to the power of minus 2, we start seeing these blank gaps. So effectively, we cannot represent numbers between the two pink bars. And the same applies here, obviously. And for bfloat 16, because we allocate even less bits, the same applies here. And the story is more extreme for 8-bit precision, because we allocate only so few bits. For example, for float 8, that uses 5 bits for exponent and 2 bits for mantissa, and obviously 1 for sign, you have only 3 unique values between 1 and 2. So the computer cannot represent any other numbers but these 3 in this interval. Looking at the very top part of the plot, so here you can see the range that different data types cover. Full precision, or FP32, spans 80 orders of magnitude. So it can represent effectively any number from 10 to the power of 40 to 10 to the power of minus 40. And obviously, we're not that interested in very big numbers. We're much more interested in very small numbers, closer to the left part, because if you have printed or just debug the neural network during its training, you can notice that gradients and for weights and activations are relatively small numbers. So you should be very careful with the small numbers that if you are trying to decrease the range, because for example, float 16 sacrifices a lot of range. It cannot, for example, represent the number 10 to the power of minus 10. There is like just nothing. But because Google Brain did this optimization and trick with reallocating some of the mantissa bits to exponent, it maintains the full numerical range. So it can represent, again, anything from 10 to the power of minus 40 to 10 to the power of 40. But again, it sacrifices the resolution. Yeah, so that's basically all the information I wanted to share here. And if you open the original good old mixed precision paper, there is two plots that I really like, and they help you understand why we can't just decrease the precision for some of the computations. So what they have done is that they trained either one or two models, I don't remember. So one of them was for Mandarin, either text-to-speech or speech-to-text. And another one was SSD, which is an object detection model from the past in the computer vision domain. And they trained them in full precision in FP32. But they have collected the values of the weight gradients and activation gradients. Thus, we have two plots. On the left is weight gradient histogram, and on the right, you can see the activation gradient values histogram. And then they analyzed if we just downcast the full precision into half precision, what values will become zero? Because again, FP16 cannot represent very small numbers. And for the weight gradients, it's not that critical. Yes, you will lose some of the values. So all of these values to the left of the red line will become effectively zero in FP16 because, as explained here, they simply, this data type cannot represent very small numbers. So everything from 10 to the power of minus 14 to 10 to the power of minus, say, 4, I don't know, 5 maybe, will not be stored. It's simply impossible to store in this data type. It's not that critical for weight gradients, but for activation gradients, which are even smaller, we see that most of the histogram lies to the left of the red line, of the red bar. So all of these values will become zero in FP16. Thus, basically, when you are doing training, you are not updating or not propagating any of the gradients back to the lower levels of the model. And to the right of the right bar, you can see the FP16 representation range, which spans from 2 to the power of minus 24 to 2 to the power of 15. So all values between this red line and this black line could be represented. Everything to the left of it, except the zero bar, cannot. And you will be losing these computations. So what to do? We will cover this solution to this problem shortly after. I mentioned one very important caveat is that these histograms were recorded for relatively old architectures. I'm not sure they're used right now. And obviously, this might be a little bit different for current generation LLMs, especially very deep models consisting of multiple levels, multiple layers, one on top of another. And I tried to make a codecs to reproduce these histograms, but for example, Llama 1B, and it nailed the task. But I decided not to share because I wasn't able to allocate enough time to proofread all the code that it produced and to put my name on it and say, hey, these are actually the gradients for the histograms for the gradients for Llama 1B fine-tuning. But basically, the story was the same. There were a lot of values, especially for the activation gradients that were out of the FP16 representation range. So yeah, I was interested in answering the question whether we can fix this simply by turning a float point 16 into bfloat 16. And I came up with this example. So let's assume you have large, quote unquote, tensor, which is just one, and we want to accumulate a lot of very small numbers to it. And again, this is connected to our computations here where we accumulate over the vocabulary size. So here we will be, in order to compute the softmax, as you remember, we need to compute the scores and then probabilities for all the tokens in the vocabulary. And this will be the numerator for the softmax. So yeah, thus we need to simulate the accumulation of huge amount of very small numbers. Let's assume that our tiny val is 2 to the power of minus 8. And let's imagine that we want to add this number to itself 2 to the 8 power of times. So effectively, if we sum up 1 with this very small number, this number of steps, we could expect 2. But there is two ways of doing that. So the first one is naive, where we iterate number of steps, and then we at every step we do the addition of this tiny tensor. And another one is blockwise, where you first of all accumulate all the small numbers all together and then do the final addition, which is the original one and this accumulated number. And if you print the results, you might expect that they should be similar. Both operations, both ways of computing the values could be equal to 2, but actually no, this turns out not to be true. Because we are computing iteratively a sum of large tensor or large number one and very small number, this operation here effectively does nothing. So every time we add something to naive sum, something tiny, this effectively results in not updating the value. And at the end, you can see the result will be 1, even though we are using bfloat 16. So not all problems could be solved just by switching the data type, and you sometimes need to think real carefully what data types you use to do the computations, in what layers, and check the results manually. So getting back to this fused LM head and cross entropy, so I decided to explain different.
Could I ask a question? Like going back
Yeah.
to the previous slide. So,
Yeah.
do we know what happens inside of torch sum that it can calculate the sum properly?
Oh yeah, we know. So the main difference here is that when we do the summation here, we're summing up all the small numbers. So when you add a very small number to another small number, there is no problem if they have the exact same exponent. So this is just like how the compute units are doing the computations. If the exponent is relatively similar, it's on the same scale, well, the summation works. But if it's very different, and in this example, the difference between 2 to the power of minus 8 and 1, the difference in exponent is 8, but we allocate only so much bits for the often for
Oh, okay, yeah. Okay, now I got it. Thank you.
yeah. So in order to do this computation of the summation here, the computer has to shift the bits in the binary representation of the number to align the exponent, and like effectively the number becomes 0 because of that.
Yeah, and in case of torch sum, does it mean that they do some kind of divide and conquer stuff? So I mean, like if you keep accumulating small numbers, at some point the computer will have to switch the exponent, right? So
Yeah.
we'll face the same problem unless we do some kind of divide and conquer stuff.
Yes. So that's definitely true. And I believe if you put, for example, here instead of 2 to the power of minus 8, 2 to the power of minus 15, for example, this will not work. I guess that's my intuition. uh, Unless there is some blockwise computation happening under the hood. So, for example, it computes partial sums for left half of this tensor and then right half of this tensor, and it repeats this recursively, as you said, divide and conquer. So I'm actually not sure how this works under the hood. My intuition suggests that it works tile-wise. So this huge tensor is divided into the tiles with some shape, for example, 256, and then it does the computation, the summation within this block. Then the next block, and then these two blocks get merged into one. If this intuition is true, this means that yes, if you decrease this value significantly, it will stop working, because at some point the running sum will be very close to 1 or some other extreme value. I mean, extreme for this specific case, and then all the consecutive additions will not affect it.
All right, yeah, makes sense. Thank you.
Yeah, so getting back to this optimization of fusing LM-Hat and cross entropy. So the authors note that most of the models nowadays are trained in bfloat 16. But the problem is that the vocabulary size for the models is relatively huge. Like it could range from, for example, 50 or 60,000 for some models to 256,000 for gamma models. And because we are using bfloat 16, and it has only 6-bit fraction devoted to representing the values uh, for the computation. And when you compute the softmax, you do the summation over in order to compute the numerator. So we know that any value below some constant, which is 2 to the power of minus 12, will likely be ignored due to truncation in the summation or rounding into normalization. That's exactly what I have shown here on this slide. And what this means is that most of the entries in the vocabulary will not contribute to the gradient computation. They will not update anything. And Analytically, this means that for any column, at most 1 divided by this constant to the power of minus 12, or 4096 entries have non-trivial values that contribute to the gradient computation. So all other values could be discarded, and this will not affect the computation, and like they will be exactly the same if your training can be float 16. But empirically, when analyzing, I believe, again, Gemma 2 model, they found that only like even smaller number of entries contribute to the gradient. Only 0.02% of elements are non-zero in the numerator when we sum up all the values for the softmax formula. And so it's very sparse. And we should not do a lot of computations. We can just ignore them if we know where to skip the computations. But luckily, this is very easy to optimize because you can just compare to 0, and if the values are 0, you just discard them and do not update anything. So yeah, that concludes the kernel part. So again, what we covered here is that you could discard a lot of probabilities and log probabilities and scores during the LM head computation. You just need a running sum that updates the numerator for softmax, and you need the probability for the ground truth token. And if you optimize that and just reorder the computations a little, include the skip of the updates where you know in advance that updates are just zeros. Sorry, I dropped something. So yeah, if you know that you can skip a lot of computations, you skip them, you are not updating the gradients, thus saving the compute time. Now we are moving to a little bit, so this paper was introduced recently, as I explained. It's like modern approach. It's adopted by maybe not most, but some of the libraries. For example, Unsloth.ai library uses this optimization under the hood, which saves a lot of memory and allows you to train bigger models or the same models with bigger batch on the same number of GPUs, on the same number of gigabytes of memory. But I want to talk a little bit about the past, how it used to be. And there is this paper from NVIDIA folks, I believe, called Mixed Precision Training, which just wanted to understand if we can naively downcast the values from full precision to half precision and train the model. So they found out that you can't really abandon the full precision computation, and at least some part of it should be done in full precision. And this is what we extensively covered on the very first lecture again, where we have a master copy of the weights. Some of the computations are happening in half precision, but just before you update the weights with the gradient, you cast them in the higher precision, do the computation in full precision, which is named here weight update, and then scatter these updated weights for all the nodes that are doing the computation for the next step, where you again do the downcast, computation, accumulation in higher precision. That was the original idea. It's still up to date. This part of the paper did not age at all, because even for FP8 calculations, as we cover in a bit for DeepSeek, they were using the same technique where you have a master copy of weights, which is stored in full precision, and you're doing some of the computations in different data types. So TLDR, you cannot do everything in one precision. In lower precision, there is something that should be done in full precision. We have already covered this histogram of gradient activation gradients on the left. But what I wanted to also highlight is that some time ago, there was this popular technique to fight against this called loss scaling. It's not that relevant nowadays. I can't recall if any of the modern day LLMs were trained with gradient scaling, because this trick was used solely to fight the FP16. So it's not a problem. So it's not a solution for BF16, for example, because there is no such problem, because the range that BF16 covers, as we have seen, is exactly the same as the range of full precision, which spans 80 orders of magnitude. But for FP16, gradients tend to be much smaller. I mean, this is true not only for FP16. Gradients tend to be much smaller than 1, and they are thus at risk of underflow. So if you decrease the precision, underflow could happen, and underflow is cutting off this part of the histogram, as we have already covered, when the number just cannot be represented in the computer. And a simple yet effective strategy that was proposed in 2017 is to scale the loss before the backward pass and then scale the gradients after. And it might seem a little bit tricky, but if you just look at the signature and this histogram, you probably could be able to figure out what's happening under the hood by the name of the method, loss scaling or scaling the loss. So essentially, as we can see, we are operating on the scale of values of logarithm with the base 2 of the magnitude of the gradients. And the problem is that everything to the left of the red line cannot be represented. But what happens if we just multiply all these values by some constant, thus shifting the histogram to the right? So everything from -60 to say -10 may be we might be able to represent it within the range of from -24 to 15. And the idea here is that, well, let's just multiply loss value. And instead of, for example, writing a loss of 1 point something something, we will multiply it by 4096, and we will like get a really huge loss. But all the gradients will also be huge. They will be like much greater than 1. And thus, we are able to use this part of the representable range of FP16. So we're effectively just shifting the histogram to the right, effectively multiplying all the values to some power of 2. And how this method worked is that you have some init scale, which is like initial value. You try this. If you get underflow or overflow is when the number is very large and cannot be represented, so it goes right here. And underflow is what I explained, is when you are to the left of this red bar and you become 0 in FP16. So you obviously can easily write heuristics to detect both these cases. And if you fall into overflow, you just use Bekoff factor. You just divide your scale by 2. If you're underflowing or most of your values become 0, you just apply growth factor, which is default of 2, and just shift this histogram 1 bin to the right, if that makes sense. And you do this several times, and then you will find init scale that just works for you. So for different architectures at different steps of the training procedure, it could be different, but the key idea is that we're just shifting the histogram here and there, and then doing then scaling in order to keep up with the mathematically correct computation of the gradients. But again, loss scaling is a relatively old technique. It's not widely used right now, and they're just covering it here for the sake of broadening the scale of knowledge. Moving on to the more extreme quantization techniques that are applied nowadays. DeepSeek is the first public report. DeepSeek v3 model is the first public instance of training the model at this scale in this extreme precision. Although I believe frontier companies like OpenAI and Anthropic have adapted this method long before them, like maybe half a year or even a year in advance. And this was all possible because how the Hopper chips were designed, the NVIDIA H100 and the H800s that DeepSeek has used. So they support FP8 naively. The flops, the number of operations that the GPUs were able to perform in FP8 is significantly higher than in full or half precision. Thus, you just naturally want to use them. So what the Chinese people have done is that they carefully analyzed each operation in the forward and backward passes, and similar how we have seen with mixed precision training in BF16 or FP16. So some aggregations and master arrays are kept in higher precisions, where some of the computations and the most intensive part of the computation, which is matrix multiplication, is done in FP8 using tensor cores, which are good fit for this mathematical operation. So mental model is this. We say we do FP8 pre-training, but actually what we mean is that we use 3 different data types in order to do the training. You can see that we have master weight copy here in FP32. The input and input gradients and some other variables are in 16-bit precision, but in order to do the computations, we downcast them to FP8, do the computations, then expand back and do the addition here in higher precision. So it's like a hierarchy of precisions. Computation is the lowest precision, intermediate accumulations, and some of the outputs are in half precision, and the master copies in full precision. In the book, they also covered the tiling and online quantization. I will not cover them in this presentation, but I wanted to devote like 2 or 3 minutes to this a really clever trick of increasing accumulation precision. Again, DeepSeek have found. So they tried to implement this naive way. I mean, and by naive, I mean this exact specific thing. And they found that the accumulation precision of FP8 games on NVIDIA H800 GPUs is limited to retaining around 14 bits, which is significantly lower than full precision accumulation. And what this matters is that how the kernels that are exposed to you by NVIDIA are designed. So they expect that some of the inputs will be in full precision, for example. Then under the hood, they do this online quantization where they cast them to FP8, do some computations, and then they scale them back to half precision or full precision. And if there are multiple of elements that you provided to this operation, to this kernel, well, there will be some accumulation, right? So for example, you can compute the first group, then the second group, the third group, the fourth group, and then you sum them up. And the problem is that this intermediate buffer that is used to accumulate the results before the kernel returns the value, they were advertised and documented as full precision, but actually turned out to be not full precision. So empirically, what DeepSeek has done, and it's very interesting, is that they design the inputs for the kernels in such a way that they are grouped as 4 operations. And they do 4 operations in one single kernel, in one CUDA kernel call, get the accumulation in low bits. Then they pull this result into the just regular CUDA cores, not tensor cores, not lower precision cores, expand them to full precision, and then do the accumulation there. So why this works is that once in a while, once in every 4 accumulation steps, you do the accumulation in full precision so that you're not losing a lot of precision against the baseline, against the full precision training. I hope that makes sense. We still have 4 minutes and I have 1 slide, but if you have questions about this slide, please ask. Okay, then to the last slide. Obviously, we want to go even deeper. So maybe instead of using 4 bits for representing one float value, we could be using 4 bits, so even less. And it's, I would say, relatively experimental for training. And it's widely adopted for inference since OpenAI has released their 120 billion GPT OSS model. They use an FP4 format, which is not just bare FP4 format, as you can imagine, but it's rather a quantization scheme where you have a lot of additional scales that are carefully adjusted for parts of the tensors so that they are not losing too much precision representing the numbers. So the book says that projecting further into the future, Blackwell, the next generation of NVIDIA GPUs, have been announced to support FP4 training, further speeding up training, but without a doubt also introducing a new training stability challenges. And NVIDIA has already done pre-training with these Blackwell GPUs at the 12 billion scale and more than 10 million trillion training tokens, which is seems promising. Maybe this year, the frontier companies will be training trillion scale models with this. It's not, it's 1/8 of the precision. So it's not half precision, it's not 1/4 precision, it's 1/8 of the precision. And the incentive here is that the lower the precision, the more values you can copy at once into the very fast memory in your GPU. So the less iterations you need to produce the same memory footprint in order to start the computations, but the computations themselves are also more optimized for the specific lower precision formats. And as you can see, if we take FP8 amount of compute that H100 has for FP8 format, Blackwell GPUs provide 5 to 7 times more compute in FP4. So most of your computations could be significantly sped up if you find a way to reduce the precision. And this is very desired, obviously, because you can train the model significantly faster or train them for longer. Unfortunately, even in this NVIDIA paper, they report that there is some loss discrepancy against the even FP8 baseline and obviously against the full precision baseline. The increase in loss probably will be even higher. But because you're training the models faster, maybe you can train for longer. So for example, instead of training for 10 trillion tokens, you can train for 12 trillion tokens and achieve the same result. And it will be better, it will be faster as measured in the vol clock anyways. Yeah, this is last slide, but basically just I try to depict the state of the industry, not even right now, but like some years ago. So software and hardware are closely tied and they are co-designed. On the right, you can see the screenshot from Twitter of one of the leads of compute at OpenAI. So they say that 3 years ago, they finalized their wishes for Blackwell GPUs and they sent them over to NVIDIA guys. So they designed the kernels, the CUDA cores, the memory hierarchy, the sizes of the buffers, the caches, etc., everything considering the requirements from their biggest customers, including OpenAI, no doubt, Anthropic, Google, etc. Or some other key players are also affecting the decisions that NVIDIA is doing. So yeah, so some of the decisions that were done like 3 years ago, 2 years ago, we just can see starting to see them now. And I'm really curious what will be the state of the industry and the optimizations and the quantization techniques in like 2 or 3 years, where the industry will catch up with some research that are people are doing right now or have done in the past like 6 months. And one example of this is that if you understand how the self-attention is computed on the GPU, there is this special function unit which is doing the exponentiation. It can be done on a regular CUDA course, or rather, it will be less effective. So, for example, I believe Tridao or some of his peers, the creator of Flash Attention, Tridao, so they found out that they are bottlenecked by the amount of exponentiation that they could be doing in one in some time. So it's not like memory, it's not compute, it's like this specific part. So the NVIDIA is listening to this feedback, and for example, Blackwell Ultra GPUs by NVIDIA, they're increasing the amount of units that will be doing the exponentiation for softmax. So simply because this will unlock one of the bottlenecks and shift the bottleneck again to the course or the CUDA course or memory or some other thing. And so yeah, it's just a race where you are trying to resolve the current bottleneck and see what's the next bottleneck. This concludes this talk. Thanks for listening. I believe not all the topics were explained really in depth because I had so much material to share with you. So for example, like we haven't covered the in-depth quantization that DeepSeek has proposed and why this is called NVFP4, but just not FP4. There is also a story behind this. Like, again, this is just type of quantization, not just FP4 value. But anyways, thanks everybody for attending the reading club for all the 3 months or even like 4 months that we spent here. Thanks to Andre for organizing this stuff and reading some of the lectures. Yeah, thanks for inviting.
Right, yeah. Igor, thanks for presenting, and yeah, once again, guys, and special thank you, Igor, for like being with this club and reading the book. So for now, we're going to wrap up this book. We're going to finish the deep dive, like the intensive course on the agents, and then we'll announce a new book, and hopefully we'll have Igor presenting again. Well, once again, Igor, your presentations are marvelous. So looking forward to learning something from you again. And yeah, all right, guys, I'm stopping the recording.